Hello everyone, thank you for coming this talk. The title of this presentation is TONIC towards Oblivious Neural Inference Compiler. In this talk, I will introduce a framework named TONIC, which can convert pre-trained models into privacy-preserving inference programs. I'm the presenter, Po-Hsuan Huang. As the outline shows, first I will talk about the background and motivation. Next, I'm going to show you our approach and the design considerations. Then the evaluation part will give you the performance result and a comparison between our effort and previous work. Finally, I will summarize this work in the conclusion. After the presentation, there is a Q&A section in the end. Deep learning as a service is common nowadays. Most of them did not consider the privacy a big issue. However, it is dangerous to share data to the internet directly without protection. Take the medical DL service as an example. Here we show two traditional schemes for DL service. In the A situation, the user uploads the sensitive data to the server and wait a prediction result. The other one is B. The model provider opens the pre-trained model's weight to the public, so the user can run the inference locally. In these two cases, we can find that both are leaking the important data. That is, user may put the sensitive data in the risk, and the model provider, on the other hand, lose their production with huge effort. Should we preserve the data? Most people will answer yes. But how? To preserve the privacy during the neural network inference, three possible solutions are listed in this slide. The ideal situation is to find a trusted third party as the middleman to perform inference after collecting the inputs from the user and the model provider. However, this ideal system does not exist yet. Practical solutions are asking cryptography for help. For example, secure multi-party computation is used to solve this problem, and the participant cannot know further data from the outside. Besides Smpc, homomorphic encryption is also a path to privacy-preserving inference, and we will talk about it later. Two programs are run at the same time when using Smpc to perform inference. The communication between them follows specific protocols. We defined inference program using Smpc protocol as Oblivious neural inference. Smpc protocol helps access the data in secure mode during the computation. The famous protocol of Smpc is Yaw's scalable circuit. In this protocol, there are two roles, scabbler and evaluator. The former generates garbled truth table and send them to evaluator. The latter evaluates the secure function with garbled table and tables. An example of garbling an AND gate is shown as a figure. Another protocol is GMW. It is different from GC by using sharing-based scheme. An input will be separated into two parts and held by two participants. Arithmetic sharing is based on GMW, but on integer domain, so it is limited to do linear operations. For example, addition, subtraction, multiplication. Here we show a small example about how it works on an AND gate. Party 0 shares X into x0 and x1 and send x1 to party 1. And party 1 do the same things. Add gate is done locally, and to reveal the result Z0 and Z1 are sent back to reconstruct the result. To do privacy-preserving inference, several efforts has been done, and we make them into 3 categories. The first one is general purpose Smpc framework. Some work build framework to support various applications, and inference is one of these applications. The user of these frameworks can develop a Smpc program without cryptography knowledge. However, they need to learn how to use the language defined by this framework. Typical frameworks are ABY, ObliVM, and so on. The second type is handcrafted design Smpc inference program. The advantage is that the execution speed is usually the fastest. However, it loses the scalability to support any new deep models. The third type uses automatic conversion technique. Any new model can be converted to privacy-preserving program without manual effort. Here we take ngraph HE2 as the example. They use ngraph to parse a given model, and the HE backend generates the program that work with HE protocols. Homomorphic encryption is different from Smpc. HE scheme can offload the computation to server. The client only needs to encrypt the input and decrypt the result. However, HE has huge costs on evaluating nonlinear operations. For example, compare the relation of two inputs. Previous work cancels the support of nonlinear operation, or send the intermediate result to the client directory. Canceling the support may cause the model must be retrained first. Sending the intermediate result to client may leak the privacy of weight. In fact, modern neural networks have nonlinear operations to act as activation function, as this slide shows. So it is important to support this operation and preserve the privacy at the same time. Our approach is not using HE, but Smpc as our privacy-preserving backend, and we choose TVM, a script compiler, to parse given model, because TVM supports much more front-end frameworks. Moreover, it has clear architecture to do optimization on different levels. All we have to do is develop the backend module to generate corresponding targets. Two targets are chosen to be responsible for inference with Smpc protocols. Following diagram are their toolchains. ObliVM is a Java-based language for GC protocol. ABY is a C++ based and contains 3 protocols that we have talked previously. To build the connection between TVM and the two targets, there are several considerations. The first one is the data type support. Generally, NN models are trained with floating point numbers. We must find corresponding type in the low-level targets. ObliVM provide private floating points. Because GC can do bitwise operations. In ObliVM, we decide to use arithmetic sharing to do most linear operations, so we need to use fixed point instead. SIMD is supported in ABY, which can reduce the memory footprint as well as make the execution faster. It is good news for inference program because there are many players can benefit from this property. For example, convolution layer can be easily optimized to SIMD friendly by TVM. Finally, supplement functions are used to help switch among different protocol and plaintext. Previous slide shows the static item in a generated program. In this slide, I'm going to describe how we make the converter and the considerations. The built-in backend of TVM can generate the low-level target code from an NN model. The layers are separated into individual functions. With this way, the protocol can be easily mapped to the functions. We just need to add a conversion between the functions if they use different protocols. During our testing, we find the code size is a big issue if the target is Java. One large layer will be expanded to a function with many statements by ObliVM compiler. We figure out the problem is caused by the SSL phone in ObliVM. So the ObliVM backend is changed to generated SSA phone ObliVM language to prevent the expansion. We also find a memory issue during the runtime. The reason of this issue is the program converts all weights into private mode at the beginning, so we introduce a new method to input from weights layer by layer. I will talk about the detail later. The first item is layer by layer translation. We can see the example in this slide. A simple model will be passed to TVM IR by TVM. TVM IR contains different functions with concrete body for the input layer. Then we use TVM IR to generate two targets for Smpc inference. The generated function will like this. There are three protocols in ABY, and we decide to take two of them after reading related papers and experimenting on ABY. Arithmetic sharing is used as more as possible. When processing the nonlinear operations, the supplement function is called to switch to YAUS GC. As the figure shows, to reduce the memory peak, the Smpc program converts the weight to private mode layer by layer. When the layer 1 finishes, the useless private variables are freed. After constructing the framework, we list the benchmarks which are used by previous work. Two datasets are used to show the scalability of our framework. For MNIST, 4 models with different architecture are used. For ImageNet, we use MobileNetV2, the same model used by ngraph HE2. to evaluate our performance. This chart shows the position of our framework with ABY backend. We can see encrypted work is super fast, but TONIC can support new model immediately. Next is the comparison between two targets. Although ObliVM has 14 points, it needs to do all operations in bitwise level. ABY has arithmetic sharing and achieves about 1,000 times faster than ObliVM. Finally, we can see the performance about scaling to a big model. TONIC is about 2.5 times faster than ngraph HE2. There are 3 points in the summary. In this work, we propose a compiler framework TONIC to convert automatic with scalability. Given a pre-trained model, TONIC is able to convert one of two targets, ObliVM or ABY. The single inference latency of Smpc by TONIC is faster than the inference time by the previous work ngraph HE2. To conclude, our framework TONIC is useful and important for privacy-preserving inference service. Thank you for listening. Any question?